When we examine Earth's position in our solar system, we encounter a series of parameters so precisely calibrated that they challenge our understanding of cosmic coincidence. The distance from our Sun, approximately 93 million miles, sits within what astronomers call the habitable zone or Goldilocks zone, where water can exist in liquid form. But this is just the beginning of a pattern that becomes increasingly difficult to dismiss as mere chance. Consider the orbital mechanics first. Earth's orbit maintains an eccentricity of just 0.0167, meaning our path around the Sun is nearly circular. This translates to a temperature variation of only about 7 degrees Celsius between our closest and farthest points from the Sun. Most exoplanets we've discovered show significantly higher eccentricities, leading to dramatic temperature swings that would make complex life development extraordinarily challenging. The precision extends to our planet's axial tilt. At 23.5 degrees, Earth's obliquity creates our seasonal patterns while avoiding the extreme climate variations that would occur with a more pronounced tilt. Mars, for comparison, experiences axial tilt variations from 15 to 35 degrees over geological timescales, creating ice ages and warming periods that would repeatedly sterilize any developing biosphere. But perhaps most intriguing is the role of our Moon. The Moon's gravitational influence stabilizes Earth's axial tilt, preventing the chaotic tumbling that would otherwise occur due to gravitational perturbations from Jupiter and other planets. Without this stabilization, Earth's climate would undergo extreme variations incompatible with the steady conditions necessary for complex life to emerge and persist. The Moon's origin story itself presents puzzles. The giant impact hypothesis suggests that a Mars-sized object called Theia collided with early Earth, ejecting material that eventually coalesced into our Moon. Yet the precise parameters of this collision, the angle, velocity, and timing, would need to fall within an extraordinarily narrow range to produce a moon of the right size and orbital characteristics to serve as Earth's climate stabilizer. Statistical analysis reveals the improbability of these coincidences. The Drake equation, formulated by astronomer Frank Drake, attempts to estimate the number of communicating civilizations in our galaxy. When we plug in conservative estimates for factors like the fraction of stars with planets in habitable zones, the probability of life developing, and the likelihood of intelligence evolving, we get numbers that suggest either we're extraordinarily lucky or there are factors we haven't considered. Recent discoveries in exoplanet research have only deepened this mystery. The Kepler Space Telescope and other surveys have revealed that most planetary systems look nothing like ours. Hot Jupiters, massive planets orbiting extremely close to their stars, are common, as are systems where planets have been scattered into highly elliptical orbits through gravitational interactions. Our solar system's architecture appears almost uniquely stable. The gas giants Jupiter and Saturn occupy positions that act as cosmic vacuum cleaners, sweeping up asteroids and comets that might otherwise bombard the inner planets. Jupiter's migration patterns in the early solar system, as suggested by the Grand Tack model, may have prevented the formation of super-Earths in the inner system while allowing smaller, rocky planets like Earth to form. The chemical composition of our solar system also shows remarkable fine-tuning. The metallicity, the abundance of elements heavier than hydrogen and helium, falls within the narrow range necessary for rocky planet formation while avoiding the extreme metal-rich environments that produce only massive, uninhabitable worlds. Our Sun's spectral class, G2V, represents less than 10% of all stars, yet may be optimal for supporting life due to its stability and longevity. When we examine the timeline of Earth's development, another layer of apparent design emerges. The emergence of photosynthesis, the oxygenation of the atmosphere, and the evolution of complex multicellular life all occurred within timeframes that allowed for the development of technological civilization before our Sun begins its expansion into a red giant phase. A delay of just a few 100 million years in any of these developments might have prevented the emergence of intelligent life. The concept of fine-tuning extends beyond Earth to the fundamental constants of physics themselves. The strength of the electromagnetic force, the mass of the proton, and the cosmological constant all appear calibrated to allow for the existence of stars, planets, and ultimately life. Even slight variations in these constants would result in universes where atoms cannot form, stars cannot ignite, or the cosmic expansion prevents galaxy formation. This brings us to the anthropic principle, the idea that we observe these precise conditions because we exist to observe them. The weak anthropic principle suggests that the universe's properties are constrained by the requirement that it must be compatible with the existence of observers. The strong anthropic principle goes further, proposing that the universe must have properties that allow life to develop at some point in its history. Yet, even within the framework of the anthropic principle, our solar system's characteristics seem unusually well suited for not just life, but for the development of a technological civilization capable of space exploration and scientific discovery. The presence of easily accessible fossil fuels, a large moon that creates predictable tides and inspired early astronomical observations, and the transparency of our atmosphere to optical wavelengths all contribute to conditions that seem optimized for the emergence of science and technology. Some researchers have proposed that we might be living in a simulation where the apparent fine-tuning reflects the parameters chosen by our simulators. Others suggest that we exist in a multiverse where countless universes with different physical constants exist, and we naturally find ourselves in one compatible with our existence. But there's another possibility that deserves serious consideration. What if the fine-tuning we observe isn't the result of cosmic coincidence, anthropic selection, or simulation, but rather evidence of intelligent design on a cosmic scale? What if an advanced civilization, perhaps one that arose in our galaxy billions of years ago, deliberately arranged the conditions that led to Earth's habitability? This hypothesis might sound like science fiction, but it's worth examining the mechanisms by which such cosmic engineering might be possible. Advanced civilizations might possess technologies that allow them to manipulate stellar evolution, direct the formation of planetary systems, or even modify the fundamental constants of physics within localized regions of space. The evidence for such intervention might be subtle, embedded in the very structure of our solar system in ways that would only become apparent to a civilization advanced enough to recognize the engineering. The implications of this possibility are profound. If our solar system is indeed artificial, it suggests that intelligence has played a role in shaping the cosmos on scales far beyond our current comprehension. It raises questions about the purpose of such engineering, the identity of the engineers, and our own role in this cosmic design. As we continue to discover exoplanets and study the formation of planetary systems, we're gathering the data necessary to test these ideas. If our solar system is truly anomalous compared to the general population of planetary systems, it might provide evidence for artificial origin. Conversely, if we discover that Earth-like conditions are more common than we currently believe, it might support more conventional explanations for our existence. The search for biosignatures on exoplanets might also provide clues. If life is common throughout the galaxy, it would suggest that the conditions for its emergence are more easily achieved than we thought. If life is rare, it might indicate that the fine-tuning we observe is indeed exceptional and possibly artificial. Regardless of the ultimate explanation, the apparent fine-tuning of our solar system forces us to confront fundamental questions about our place in the universe. Are we the product of cosmic coincidence, anthropic selection, or intelligent design? The answer to this question will shape our understanding of life, intelligence, and the cosmos itself for generations to come. The revolution in exoplanet discovery has revealed a universe far stranger and more diverse than we ever imagined. Since the first confirmed detection of an exoplanet orbiting a Sun-like star in 1995, we've cataloged over 5,000 worlds beyond our solar system. What emerges from this census is a troubling realization. Our solar system appears to be profoundly atypical. The most common type of exoplanet discovered is something that doesn't exist in our solar system at all, the super-Earth. These worlds, with masses between that of Earth and Neptune, are found in roughly 30% of all planetary systems. They typically orbit much closer to their stars than Earth orbits the Sun, completing their years in just days or weeks. Yet our solar system contains no such planets, despite their apparent ubiquity elsewhere. Even more perplexing is the prevalence of hot Jupiters, gas giants that orbit extremely close to their parent stars. These massive worlds, with surface temperatures exceeding 1,000 degrees Celsius, represent approximately 1% of all exoplanets discovered. While this might seem like a small fraction, their detection is heavily biased toward easy-to-find systems. The true prevalence of hot Jupiters is likely much higher, making our solar system's configuration with Jupiter safely positioned in the outer system increasingly unusual. The spacing of planets in our solar system follows patterns that aren't commonly observed elsewhere. The Titius-Bode law, which describes the semi-regular spacing of planetary orbits in our system, appeared to be a fundamental principle of planetary formation. Yet, exoplanet systems rarely follow such orderly arrangements. Most show evidence of chaotic migration, gravitational scattering, and orbital instabilities that would have disrupted any Earth-like world attempting to maintain stable conditions. Consider the case of Kepler-36, a system where two planets orbit so closely that when aligned, they appear larger than the Moon does from Earth. Such gravitational interactions would create tidal forces and orbital perturbations incompatible with stable climates. Or examine HD 80606b, a planet on such an eccentric orbit that it experiences temperature swings from 500 to 1,500 degrees Celsius during each 111-day orbit. These examples illustrate the violent, unstable nature of most planetary systems. The NICE model, developed to explain the architecture of our outer solar system, suggests that our gas giants underwent a period of orbital migration and gravitational resonance that ultimately stabilized into their current configuration. This process, known as the late heavy bombardment, occurred approximately 4.1 to 3.8 billion years ago. The timing of this event appears crucial. It occurred early enough to allow Earth's surface to cool and oceans to form, but late enough that the planet had differentiated into its current structure. The precision required for this migration to result in a stable, life-friendly system is extraordinary. Computer simulations of early solar system dynamics show that slight variations in the initial conditions lead to drastically different outcomes. In many scenarios, Jupiter migrates inward, disrupting the terrestrial planets. In others, the outer planets are ejected entirely, leaving the inner system vulnerable to constant bombardment from asteroids and comets. Our solar system's stellar neighborhood also appears unusually benign. The Sun sits in what's called the local bubble, a region of space with lower than average stellar density and relatively few supernova explosions in recent geological history. This location shields Earth from high-energy radiation that would strip away our atmosphere and sterilize the surface. Most stars in the galaxy don't enjoy such protection. The metallicity of our solar system, the abundance of elements heavier than hydrogen and helium, falls within a narrow range that appears optimal for terrestrial planet formation. Too low and rocky planets cannot form. Too high, and the system becomes dominated by massive planets that prevent Earth-like worlds from developing. Recent surveys suggest that this optimal metallicity range represents only about 10% of all stars in the galaxy. The age of our solar system, at 4.6 billion years, also appears fortuitously timed. Early in the galaxy's history, the metallicity was too low for terrestrial planets to form. Much later, as the galaxy ages, the increasing rate of stellar explosions and black hole activity may make stable planetary systems increasingly difficult to maintain. Our solar system formed during what some astronomers call the galactic habitable zone in time. The discovery of circumbinary planets, worlds orbiting binary star systems, has revealed another way our system is unusual. Roughly half of all Sun-like stars exist in binary or multiple star systems. While some of these systems can host planets, the orbital dynamics are far more complex, with planets experiencing varying stellar radiation as they orbit around or between their parent stars. Our single star system provides the stable energy input necessary for long-term climate stability. The concept of planetary system architecture extends beyond just the planets themselves. The distribution of asteroids, comets, and other small bodies in our system appears carefully orchestrated. The asteroid belt between Mars and Jupiter acts as a reservoir of building materials that contributed to planetary formation while not being dense enough to prevent stable orbits. The Kuiper Belt and Oort cloud provide a controlled source of comets that may have delivered water and organic compounds to Earth without overwhelming the planet with impacts. Comparative analysis of debris disks around other stars reveals that most systems either lack these reservoirs entirely or have them in configurations that would make terrestrial planets uninhabitable. The precise balance achieved in our solar system, enough small bodies to deliver life's building blocks, but not so many as to prevent life's development, appears to be extraordinarily rare. The phenomenon of planetary migration, while observed in our system, appears to have been much more gentle than in typical exoplanet systems. Most systems show evidence of violent migration events that scatter planets into highly elliptical orbits or eject them entirely. The Grand Tack model suggests that Jupiter migrated inward to approximately $1.50 before reversing course and moving outward. This migration cleared the inner system of super-Earths while allowing smaller, rocky planets to form in the habitable zone. The timing and extent of Jupiter's migration appears to have been perfectly calibrated to create the conditions we observe today. If Jupiter had migrated too far inward, Earth would never have formed. If it had migrated too far outward, the inner system would have been populated with super-Earths unsuitable for life as we know it. The precision required for this migration pattern suggests either extraordinary luck or deliberate design. Recent studies of white dwarf stars provide additional evidence for our system's uniqueness. When stars like our Sun die, they shed their outer layers, revealing the rocky debris of their former planetary systems in the spectrum of the resulting white dwarf. Analysis of these stellar graveyards shows that most planetary systems contained far different compositions than our own, with different ratios of rock-forming elements that would have produced planets unlike Earth. The chemical evolution of our solar system also appears to have followed an unusual path. The solar nebula from which our planets formed contained precisely the right mix of elements to produce both rocky terrestrial planets and gas giants. The isotopic ratios of various elements in meteorites and terrestrial rocks suggest that our system incorporated material from multiple stellar sources, including supernovae and neutron star mergers, in proportions that seem optimized for the formation of habitable worlds. The concept of system-wide habitability extends beyond individual planets to the entire solar system environment. The magnetic field generated by our Sun, combined with Earth's own magnetic field, creates a protective bubble that shields the inner planets from cosmic radiation. The solar wind, while potentially harmful, also plays a crucial role in maintaining atmospheric compositions and preventing the buildup of interstellar dust that could disrupt planetary orbits. As we continue to discover and characterize exoplanets, the apparent uniqueness of our solar system becomes increasingly difficult to explain through conventional planetary formation models. Statistical analyses suggest that Earth-like planets in Sun-like systems may be extraordinarily rare, perhaps representing less than 1% of all planetary systems. This rarity raises profound questions about the mechanisms responsible for our system's seemingly perfect configuration. The possibility that our solar system represents an artificially constructed environment becomes more plausible when we consider the advanced engineering capabilities that any sufficiently developed civilization might possess. The ability to direct stellar evolution, manipulate planetary formation, and fine-tune system-wide parameters would represent the ultimate expression of cosmic engineering. The evidence for such intervention might be subtle, embedded in the very structure of our solar system in ways that would only become apparent to a civilization advanced enough to recognize the engineering. As we expand our census of exoplanets and continue to refine our understanding of planetary formation, we're gathering the data necessary to test whether our solar system is truly as unusual as current observations suggest. If confirmed, this uniqueness would represent one of the most significant discoveries in the history of science, forcing us to reconsider our fundamental assumptions about the nature of the universe and our place within it. If we seriously consider the possibility that our solar system might be artificially constructed, we must examine what such engineering would require and whether it falls within the realm of physical possibility. The technologies needed for stellar and planetary engineering stretch far beyond our current capabilities. yet they don't violate the fundamental laws of physics. Understanding these potential mechanisms provides insight into how an advanced civilization might sculpt the very architecture of space and time. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, provides a framework for understanding the energy consumption capabilities of advanced civilizations. A Type II civilization harnesses the entire energy output of its star, while a Type III civilization controls the energy of an entire galaxy. The engineering of solar systems would likely require capabilities somewhere between these scales, representing a level of technological advancement that could emerge millions or billions of years before our own. Consider the mechanisms by which stellar evolution might be controlled. Stars like our Sun burn hydrogen in their cores through nuclear fusion, with the rate of this process determining the star's luminosity and lifetime. An advanced civilization might possess the ability to regulate this fusion process, extending stellar lifetimes or modifying luminosity to maintain optimal conditions for planetary habitability over geological timescales. The concept of stellar lifting represents one approach to stellar engineering. By using powerful magnetic fields to channel stellar material away from a star's surface, it might be possible to reduce the star's mass and extend its lifetime. Alternatively, the controlled addition of specific elements to the stellar core could modify the fusion process, allowing for precise control over the star's energy output and spectral characteristics. Planetary formation occurs within the protoplanetary disk that surrounds young stars. This disk contains the raw materials that eventually coalesce into planets, asteroids, and comets. An advanced civilization might possess the ability to manipulate the composition, density, and dynamics of these disks, controlling where and how planets form with extraordinary precision. The process of planetary migration, which we observe in our own solar system and in exoplanet systems, could be artificially directed through gravitational manipulation. By positioning massive objects at specific locations, or by using advanced propulsion technologies, it might be possible to guide planets into precise orbits that optimize conditions for habitability. The Grand Tack model of Jupiter's migration, which appears so perfectly timed to create our current system architecture, might represent evidence of such directed evolution. The concept of megastructures provides another avenue for cosmic engineering. A Dyson sphere or swarm of solar collectors could not only harness a star's energy but also regulate the amount of radiation reaching specific planets. More subtle structures, such as networks of solar shades or mirrors, could fine-tune the energy balance of individual worlds, maintaining optimal temperatures for billion-year timescales. The manipulation of planetary atmospheres represents another possible engineering target. The delivery of specific gases, the regulation of atmospheric escape, or the modification of magnetic fields could all be used to maintain atmospheric compositions conducive to life. The presence of Earth's unusually strong magnetic field, generated by our planet's iron core, might represent such intervention. The precise conditions needed for a strong magnetic field are difficult to achieve through natural processes alone. Quantum engineering at the fundamental level opens even more exotic possibilities. The fine structure constant, which determines the strength of electromagnetic interactions, appears to be fine-tuned to allow for the existence of stable atoms and molecules. If the fundamental constants of physics can be modified locally, An advanced civilization might possess the ability to create regions of space where the laws of physics are optimized for the emergence and sustenance of life. The concept of closed time-like curves, permitted by certain solutions to Einstein's field equations, raises the possibility of temporal engineering. If causality can be manipulated, an advanced civilization might be able to influence the past development of solar systems, creating the conditions necessary for their own existence or the existence of other intelligent species. While highly speculative, such capabilities would represent the ultimate expression of cosmic engineering. The search for evidence of such mega-engineering projects has become a legitimate scientific endeavor. The search for extraterrestrial intelligence has expanded beyond looking for radio signals to include the search for megastructures, artificial stellar manipulation, and other signs of cosmic engineering. The star KIC 846-2852, known as Tabby's star, showed unusual dimming patterns that initially suggested the presence of massive artificial structures. Though natural explanations now seem more likely, the detection of technosignatures, evidence of technological activity by advanced civilizations, represents a growing field of astronomical research. These might include the spectral signatures of artificial atmospheric compositions, the infrared excess from waste heat of megastructures, or the gravitational wave signatures of massive engineering projects. If our solar system is indeed artificial, there might be subtle signatures embedded in its structure that would reveal its engineered nature to sufficiently advanced observers. The anthropic principle provides a framework for understanding why we might exist in an artificially constructed system. If advanced civilizations routinely engineer solar systems to support life, they might create numerous habitable worlds throughout the galaxy. From our perspective, we would naturally find ourselves in one of these engineered systems, as they would be the only places where observers like us could exist. The zoo hypothesis, proposed by MIT radio astronomer John A. Ball, suggests that advanced civilizations might maintain regions of space as preserves for developing species. Under this scenario, our solar system might represent a carefully constructed habitat designed to allow human civilization to develop without interference. The apparent absence of other intelligent species in our local region of space might reflect the enforcement of such a preservation policy. The concept of directed panspermia, originally proposed by Francis Crick and Leslie Orgel, suggests that life on Earth might have been deliberately seeded by an advanced civilization. If combined with solar system engineering, this would represent a comprehensive approach to creating life-bearing worlds throughout the galaxy. The rapid emergence of life on Earth, occurring almost as soon as conditions permitted, might support such a scenario. The Great Filter hypothesis proposes that there exists some extraordinarily difficult evolutionary step that prevents most life from developing into spacefaring civilizations. If this filter lies in our future, the engineering of our solar system might represent an attempt by previous civilizations to help us navigate this challenge. Alternatively, if the filter lies in our past, our existence might indicate that we've already been assisted through the most difficult evolutionary transitions. The Fermi Paradox asks why, given the vast number of stars and planets in the galaxy, we haven't encountered evidence of other intelligent civilizations. One possible resolution is that advanced civilizations become so sophisticated that their activities become indistinguishable from natural phenomena. The engineering of our solar system might represent such advanced technology, operating at levels of subtlety that we're only beginning to recognize. The simulation hypothesis, popularized by philosopher Nick Bostrom, suggests that our entire reality might be a computer simulation created by an advanced civilization. If true, the fine-tuning we observe in our solar system might simply reflect the parameters chosen by our simulators to create a stable, habitable environment. The apparent optimization of our system for the development of scientific civilization might indicate that we exist within a simulation designed to study the emergence of intelligence. The concept of cosmic ancestry proposes that life and intelligence are fundamental features of the universe, seeded and nurtured by previous generations of advanced civilizations. Under this scenario, the engineering of solar systems becomes a natural extension of biological reproduction, with intelligent species creating conditions for the emergence of their successors. Our solar system might represent one link in an unbroken chain of cosmic engineering spanning billions of years. The implications of artificial solar system construction extend far beyond our understanding of planetary formation. If confirmed, it would represent evidence that intelligence plays a fundamental role in shaping the structure of the universe itself. It would suggest that the cosmos is not a collection of random events, but rather a carefully orchestrated system designed to support the emergence and development of conscious beings. The search for our cosmic engineers might require new approaches to astronomical observation and analysis. We might need to look for subtle correlations in the structure of multiple solar systems, evidence of coordinated engineering projects spanning vast regions of space. The detection of such patterns would represent one of the most significant discoveries in human history, fundamentally altering our understanding of our place in the universe. As we continue to develop our own technological capabilities, we might eventually reach the point where cosmic engineering becomes possible for human civilization. The modification of asteroids, the terraforming of planets, and eventually the engineering of entire solar systems might represent the natural progression of our species' technological development. In doing so, we might join the ranks of the cosmic engineers, contributing to the ongoing project of making the universe suitable for life and intelligence. The question of whether our solar system is artificial ultimately challenges us to think beyond the boundaries of conventional science and consider possibilities that stretch the limits of imagination. Whether the result of cosmic coincidence, anthropic selection, or deliberate design, the existence of our finely tuned system represents one of the most profound mysteries of existence. As we continue to explore the cosmos and develop our understanding of the universe, we inch closer to answering this fundamental question about the nature of reality itself.